And right now, I want to continue first what we started in part one and we did not complete. I want to introduce the QT plot, or the so-called quantile to quantile plot, which is a technique that was introduced in 1968 by Wilk, actually by Wilk and Sikan. Okay. So what is this quantile to quantile plot? Suppose that we have two random variables. Uh, Suppose that we have x and y, which are random variables, and we have the cumulative distribution functions. X for we have f sub x for x and f sub y for y. Now, what we assume here is that we can find the inverse of the CDF. So essentially, we make an implicit assumption that we can find an inverse or the inverse of these CDFs. These CDFs are non-decreasing functions, but here we assume, in theory, we assume that they are strictly increasing, and if they are strictly increasing, then they are injective functions. We can find their inverses. So the parametric curve, if P is between 0 and 1, inclusive actually, then the curve with the following points is the Q2 plot of the distributions of x and y. So the main idea is the following. On the horizontal, if x and y have the same distribution, then for each p, f sub x inverse of p is equal to f sub y inverse of p, because since they have the same distribution, the distribution functions, the CDFs, are equal. In this case, what the parametric curve, which is the Q2 plot, is going to be? It's going to be exactly the diagonal, 45-degree diagonal on the square from 0 to 1. So let's see how the Q2 plot goes in practice. the ideal GQ plot is the diagonal of 45 degrees, because that's a square and didn't come out to be very diagonal here, just deviated. It's going to be this. So this is the curve if x and y have the same distribution. Now suppose that we have a data set and we want to examine whether the data set has a distribution of a kind. So we can, for example, we can use the QQ plot to test a set of data points, a set of data actually, to examine whether the data come from a certain distribution or obey a certain distribution. So in this case, we use the data, which essentially would serve as the random variable x, or if you want here, the random variable y. So let's see, we plot y here, and in this case we plot x horizontally, just to be to use what we typically do. And so why are the data points? X1 has taken the values which have been determined by the data. X is the prototype. For example, normal, it can be the normal, it can be the gamma, it can be several things. The first thing that we do is that we take the data y and we order them. So what I do, I order them not as the order, not according to according to increase in magnitude, but not as they by the indexing as they have been collected. So the 1 is the smallest number, 2 is the biggest, the bigger, the second bigger, and so forth and so on. So the parenthesis here means the index after ordering the data in increasing magnitude, with respect to increasing magnitude. And now what we do is this is the so-called ordered statistics. We mentioned that at the begin in part 1, and we use the order statistics now to create the empirical CDF of the data. So what is now the empirical CDF of the data? We have mentioned the empirical CDF before. If you look at it in part 1, I'll just browse very quickly here, and the empirical CDF from the data will have this particular graph. Here's the empirical CDF. After we have ordered the data in increasing order of magnitude, the first point, before we go to the first point, the CDF has probability 0, then it has 1 over n, and so forth and so on. Now, so f sub y is the empirical CDF. Now, the empirical CDF is non-decreasing because it has those flat points. So here we can use, since we have an ambiguity now to resolve, and actually here is the ambiguity as it arises. F sub y for any number, for any q number, and the q, if q is between the jth in order and the j plus 1, when q is between the jth in order and the j plus 1 in order elements, then the CDF, the empirical CDF, takes this value, j over n. So we can pick as the jth over nth quantile of the empirical CDF of the data, any number between these two, any q number. I don't know where's that. So many people either use this. So choices for the so-called jth over n sample quantile is either x sub j, or some people use x sub j plus 1, or some other people choose the point j minus 0.5 divided by n. So when I will go now to the vertical axis, I will mark the quantiles according to this rule. So I'll take j minus 0.5 divided by n, and I will use those numbers for the quantiles. And the quantile that corresponds to this value will be taken equal to this data point. Actually, I want to change something, and what I will change is that I will use this x for the data and y for the prototype distribution. So f sub x is the empirical CDF. So we do this. That's better because it resembles that. It fits that. So when we mention theoretically the QQ plot, we said that the QQ plot is a graph which has these points. So the first coordinate, the x coordinate, is a quantile with respect to the first distribution, and the second coordinate is a quantile with respect to the second distribution. In the QQ plot, in practice, what we do is that the first distribution are the data. The second distribution comes from the prototype distribution that we want to test against with. And for this purpose, you essentially don't see anywhere on the x and y axis the p, but here what instead of 0 and 1 you will see some values which correspond to the quantile points. The quantile points are points that are actually values of the random variable, not probabilities. So those should be values that correspond to x and to values of y. So this is exactly what we'll do here. So here is the prototype random variable, and here are the data that are being plotted. Okay, so since we are able to pick any number between any numbers, the quantile is the jth over nth quantile, sample quantile. We call it sample because it comes from the empirical distribution. In particular, we choose this value, j minus 0.5 divided by n. This is the quantile, and you will see why we do this. So we specialize this term. So I'm not going to do exactly the inverse, but what we say is that the x sub j, we assign this. Okay? So the QQ plot, now this serves as probability, SP, should be the points and since I choose those P points, then I have, say, minus 0.5 divided by n. So these are the points on the plane of the QQ plot. And that will be a curve. Actually, it will be a set of points, a cluster of points. So it will look like a scatter plot, precisely. What is the sequel? What we'll put in the x-coordinate? Well, then we put the data. This is the jth data point. So what I will do here is to put the values of my data. And I will start with my smallest one, then with my second smallest, then with my third smallest, and so forth and so on. What will be the values here? Those values will correspond to this particular. So what should be this particular value? This will be f sub y inverse of 1 minus 0.5 divided by n. What finally will be if this is the x sub n, parenthesis, the biggest of all the data points that I have. Now this one corresponds to a point somewhere here. I think that's what it needs. The data point that corresponds to this would basically fit the following. It should be a point somewhere here. Where what should I put at this particular point? What I should put at this particular point will be f sub y inverse of n minus 0.5 divided by n. So this is 1 . So this value will be the 0.95. If, for example, I had 10 points. If I have 100 points, then this is 100 minus 0.5. This is 0.995. Okay, so it can be, so it's exactly this this value there. So let's specialize with a normal probability plot. So a QQ plot that Y has the standard normal distribution or a normal distribution in general, it's called normal probability plot. And I will use a test, I will use a table that from data in the book, so we'll have some observations I will want to plot against the standard normal distribution. So what we do, those observations are the following. Let's write down, write down a few of them, and then we'll do the calculations that are necessary. I write them in ascending order. Suppose that we have those calculations. Those actually let me write them in ascending order as they are. Suppose that I had a sample with only 5 data points. So these are sample values of X. Only 5. And I want to do the normal, to make the normal plot. So use for these observations. So my Y will be the standard normal distribution here. Or a normal, I can also do a normal distribution in general, but the standard normal will be fine. It's exactly, it doesn't really matter if you use the standard normal or another normal. All this is determined upon basically what the mean of your data is. So, as you see, the data, first of all, are in ascending order. So this is exactly, if I would like to write X sub 1, for example, I would say this is my 31.3, where the highest one among the 5, the maximum value of all of those is 53.9 of those data points. Now, what I put here is, on the second column, is actually the value I minus 0.5 divided by 5, and I will run between 0, 1, 2, 3, and 5. So this is my 0.5 divided by 5. That gives me 0.25, 0.01 actually, 0.1. Then I have 2 minus 0.5, that's 1.5, that's my 0.3. This is 1 minus, 1, 2, 3, 3 minus 0.5 divided by 5. So I have 2.5 divided by 5. So this is the 0.5 point. That's my 3.5 divided by 5.7, and this is finally my 5 point, the minus 0.5, this is my 0.9. And what exactly do I have in this table? What I have in this table is the following. What I'm saying is that f sub x, what this table facilitates, let's write it below the table, is that f sub x of inverse of 0.1. This is not exactly the inverse as you did it in calculus, but it's the way I assign the inverse, because you have an empirical CDF, and the empirical CDF is not invertible because it's not strictly increasing. That table facilitates this, how I find these points. And exactly my 0.1 inverse is the inverse of value of 0.1 under the CDF I designate to be this. And I did this by using this particular equation. Since I have 5 points only, my quantiles are the 10%, the 30%, the 50%, the 70%, and the 90%. Had I not subtracted the 0.5, the last one would have been the 100%, but since I want to plot against a normal distribution or another known distribution, the last data point that I have should not always be the 100% point, because, for example, for the normal distribution, there is no point that will give you that will give the value of the CDF to be mathematically equal to 100%. So that's why we do subtract this 0.5. Now I'll look what are the corresponding quantile points for the normal distribution. So I have to look at tables of the normal distribution. I go to the CDF of the standard normal distribution because this is the one I'm plotting against. And we can look at one such table on pages 568. I'll look at 568. And I see where are the values which are equal to 0.1. Well, it takes a little bit of search here. One such point is negative 0.128. So that's what I'm going to take. 8. So these are the so-called p-values. So here, the QQ plot will be these values, and again, at that point, I'm taking f of z inverse of 0.1. An approximation, you're not going to be able to take those points precisely. My next point is what value of z gives probability to be equal to 0.3? Because that point here should be f of z inverse equal to 0.3. And that point is precisely, we'll look at the tables. It's negative 0.52. I made a mistake at the first point. That's why I was surprised a bit. It's negative 1.28. And so continuing likewise, these are the points that correspond to the inverses of the values of the z that correspond to those probabilities, those quantiles. Namely, that's the 50th quantile, which is the median. This is the 70th quantile, that value, and this is the 90th quantile. So the plot is to connect this value with this value. So that's what we're going to do here. So go to our table. We'll put 31.3, 42.2, and so forth. And here we have, and that's on this axis. Things can be as you want them. On the vertical one, you start from, typically what we do is that we do not put 0 in a way that creates something like this cross, but we just lift this axis, so we'll have negative 1.28. That's done for practical purposes. Then here you should put 0. Then you will have negative 0.52 somewhere here. So that would be 1 point in the QQ plot. That would be another point in the QQ plot. And somewhere here we should put what would be the diagonal. Sometimes software does that automatically. So what would be the diagonal had we have a full normal distribution? And if the points come from a normal distribution, then those points, they should be right on the diagonal. I'm not claiming that this is true here in this particular case, but the more close to the ideal diagonal of this table these points are, the more they represent points of a normal distribution. Data points that come from a random variable which is normally distributed. So this is the main idea of the QQ plot. So if your data were coming from a normal distribution, since your 44.5 corresponds, which is somewhere here, let's say, corresponds to it's the 50th percentile. In the normal distribution, the 50th percentile is the is actually the mean. So it should correspond actually to this. Let's make it look better. It should correspond to this. So if that's the point here, then if you take the 45-degree angled straight line, if the data come from a normal distribution, they should fit on this particular. They should be very close to this particular line. If they are not close to this particular straight line, then the data don't come from a normal distribution, but come from another distribution. And of course, they're based on on the way those points are being placed or inside this QQ plot. There are statistical tests that actually check whether the data come from a normal distribution or don't come from a normal distribution. What I have done here on this part of the table with the normal distribution, I can do with another distribution like the gamma or the exponential or even the Poisson. What we do with discrete can also be, with continuous can be done also with discrete random variables. There is absolutely no problem in doing that. Well, I guess that takes us through the QQ plot. And the final thing we want to talk about today is the generation of random number sequences and sequences that actually fit random sequences that come from sequences of random numbers that come from a certain distribution. And that's the next point, the next thing we will talk about. We continue now with the final topic of our discussion, which is random numbers, generating random numbers. This is a very, very interesting topic because it's also related to cryptography. What is cryptography? Well, you all know what is an encryption system, and an encryption system, mathematically, is a system where it takes a message. It's actually a transformation that takes a message T. M is the message. T is the transformation, the encrypting transformation. That encrypting transformation is using a key. So essentially we can say that this is a function of two variables. One is the message and the other is the key that is being used. And the key changes, is not stationary, it's not the same. And that, the mapping of the message with the key is another signal, is another message that can be transmitted can be transmitted or it can be stored in a non-secure medium. So that's transmission that can be transmitted. Everybody is allowed to know that, to see that. Now, this transformation is invertible provided that somebody knows the key. If you don't know the key, then there is no way to invert the transformation. After inverting this transformation, the one who is allowed to read the message, the authorized receiver of the message, who is supposed to know the key, can invert the message. And this is a very, very big domain of research. And there's lots of stories of research and espionage. I just briefly refer on these stories a little bit and the thrill that accompanies them at the end of this presentation. But let's go now to random numbers because that is very significant. Okay, how can we generate random numbers? Suppose that you want to generate random numbers between integer random numbers 1 through 6. Well, the best way to do it, if you want to generate a sequence of 20, let's say 20 or 30 or how many, n random numbers, the best way to do it, if you have to choose between 1 and 6, the best way to do it is to take a die with 6 sides and cast it 20 times, cast it n times. Record the numbers and that gives you a sequence of 20 numbers, 20 randomly generated numbers. Well, that's not a very, very efficient operation, but it's one way to do it. That's a very simple way to do it. You can devise other methods like drawing raffle, but it's not very good to say, well, I keep thinking of numbers and those numbers are random. That's not correct. You have to use some external device. There's an extensive way to do that, and actually modern computers produce produce random numbers by using certain algorithms, and those algorithms use a random seed. So a random seed is a reading of the clock of the computer, and the clock of the computer depends on some inputs that the computer receives from its processor. In the older times, there were arrivals of electrons were being used, arrivals of electrons from diode bulbs. So those diode bulbs were used to, in terms of, in lieu of what is today a transistor, and they had an anode and a cathode. So here was the cathode, and from the cathode you had electrons that were emitted because the cathode was being heated. Actually, they were kind of good. You could put. I mean, I saw them. I reached them in my lifetime, and actually, our first TV was full of those. It was a huge box full of those, and those were producing a lot of heat actually. So those electrons, because of the heat, were leaving the cathode wire, and they were attracted by the anode because the anode had the opposite polarity from the cathode. And arrivals of electrons in the anode could be recorded, and it can be proven that if you observe the arrival of electrons, the number of arrivals of electrons in non-overlapping time intervals, then those arrivals are completely independent of one another, and you can use those to produce a sequence of random numbers. Actually, those are random variables, and if you recall, we modeled those random variables by the Poisson distribution. However, those arrivals, when we produce random numbers, those arrivals are not modeled by the Poisson, because we don't have we don't use the same all of the same assumptions, but the independence. Yeah. Another way to do it, and it was being done, was to count arrivals of cosmic particles, or the background of cosmic radiation, the intensity of background cosmic radiation. These were other devices that were used to develop random numbers. So these days, random numbers, as I said, are produced by using a random machine. So in a computer, that's the clock of the computer, the internal clock of the computer. It's not the clock that you keep on the computer, but it's the clock of the processor. And that creates a random number, which is called a random seed. And using the random seed, we generate a sequence of random numbers by using a linear transformation, typically. And those sequences of random numbers that are generated by one random seed are called pseudo number generators. They're called pseudo number generators because you cannot produce ideally a random number sequence by using by using the random seed in a linear transformation. So suppose now that we have a way to produce random numbers, and let's say that we want now to produce 1,000 random numbers between 1 and, let's say, 20. 1 and 1,000. Actually, you can do that very easily. There is a pseudo number generator on the internet that I advise you to use. Well, actually, I advise you to check. There's been some controversy about how pseudo-random is the random number generator, but I found it today over the internet, and I have, among other things, to tell you here. Allow me. It's random.com, I think. Random.org. To random number service. And if you go to this website, you can use this, or you can go further, scroll down and see numbers, integer number generator. So that's the one you want to use. It creates random integers, but and the randomness comes from atmospheric noise. Okay, so I'm not really prepared actually to tell you what is atmospheric noise, but it's white noise generated by the atmosphere. Now, what is the characteristic of white noise? The characteristic of white noise is that whatever you generate, whatever sequence you generate during a certain time of observation, time window of observation, is independent of what you will produce in any other non-overlapping time window of observation, and the characteristics will be exactly the same. Now, the main part two, get the numbers. So if you just get the numbers here, those are 100 numbers that were generated by atmospheric noise between 1 and 100. Now, what is the characteristic of those numbers? If you produce the histogram of those numbers, or if you see the relative frequency of those numbers, then what you should observe, if you take those numbers, freeze the screen for a while and take down these numbers and observe the relative frequency in which these numbers are being produced, that frequency should be approximately equal for each one of them. And since I asked the machine to produce 100 numbers, then each one of them should appear with probability 1 over 100. Now, if we go back and we say that we want to generate 1,000 numbers, then here are the 1,000 numbers. If you are patient enough and you do the calculations of the relative frequency of all of those, then you should see that all of these numbers should approximately appear, since they're between 1 and 10, 1 and 100, and I asked 1,000 numbers, they should appear with frequency 1/10. Let's look at 100 because it's easier to pick the 3-digit numbers among them, and that's a quick test. Actually, it's not the ultimate test. You have to do it for every number between 1 and 100. So let's observe 100. How many times do we have 100 appearing here in those columns? Let's count the count per column. we should see 100 in each column. The first column doesn't have any 100 numbers. No, 100 does not appear in the first column. It appears on the very last column, the fifth column, once, actually 3 times. Then we look at the fourth column. Here's again. So I have counted already 4 appearances. Then let's look at the third column. There is 1 time in another one at the bottom, and another one here. So we have 3 more appearances, actually 4 more appearances of 100 in the third column. And in the second column, I'm looking at both first and second, so we can do it fast. I see 1 more time in the second column, and another more time again in the second column, 3 more times in the second column. Actually, I counted 4 times in the second column, so this is 12 over 100, 1000. So exactly the numbers will not come out to be the same, but there should be approximately equal to 1 over 10. And that's not a very big difference from 1 over 10. So this is the characteristic of a random sequence. Now, if I want to create a random sequence of numbers that follow the uniform distribution between 0 and 1, that would actually amount to ask for the creation of a realization of X with uniform. That's a very crucial step, with uniform distribution between 0 and 1. So now X, that random variable, is a continuous random variable, and what I create is a realization of this. Suppose that you want 1000 random numbers. So essentially what you want is to create x1, x2, x1000, all with uniform distribution between 0 and 1. Now, once I press the button and I create those, as I did before, then I have the realization of a uniform distribution. So now, after I press the button, as I did in the previous screen, I get my 1000 random numbers. Now, those numbers are not going to be integer numbers, they're going to be decimal numbers because I asked them to be between 0 and 1. And how can I create those? Well, the trick is not very difficult. I take the previous, take your integer numbers, take the realization of the discrete, as we call it, uniform distribution between 0 and actually between 1 and 100. The maximum was 100, the minimum was 1. Well, I want to be between 0 and 1, but since I did not use 0 before, what I can do is to subtract 1, so I can as well have 0, or even use between 1 and 1001, 1 and 101. So when I subtract 1, I have numbers strictly between 0 and 100. So you could have generated 1000 numbers between 1 and 1001. So now take your integer numbers and the numbers that you will create will be the number I, which is between 1 and 101, one of the 1000 numbers that you have created. Actually, this is I is from 1 to 1000 because you want 1000 numbers. We took the number n sub I. N sub I is between 101 and 1. Subtract 1. So now those differences are between 0 and 100. And divide them by 100. That gives you integer numbers, that gives you decimal numbers with a uniform distribution between 0 and 1. This is a realization. And as I said, these numbers are simply a random sample of size 1000 of the uniform distribution between 0 and 1. By gathering just the data points, the data numbers, we say that we have a realization of the uniform distribution between 0 and 1. Now suppose that I want to find a realization of the same size for a known distribution, let's say the gamma distribution or the normal distribution. So let's say now that I want realization, I want a realization of 1000 So we want suppose now that I want a realization of 1000 numbers x sub I from, let's call them y sub I. From the normal distribution with parameters mi and sigma, or with some other distribution. In general, from a distribution from with a known strictly increasing CDF cumulative distribution function f. Right, to do this, we have to observe the following. So far we know how to create U sub I, which is equal to X sub I. Those are random. This is a random sample, and the numbers, the sequence of those numbers is a random realization. With the U of the uniform distribution in the interval 0, 1. Now let's call it zero to 1. Now, probabilities are actually vary within this interval. So if we do the following, if we take the quantile points precisely, if we take Q sub I to be F inverse of X sub I, so those are similar to what we did, the quantile points, then those Q sub i's exactly are the Y sub i's I'm asking. The realization, the 1000 number realization from the distribution with the CDF cap F. Why is this correct? Well, the answer, sorry, my mother. The answer is easy and comes from the following. The answer is precisely the Q2 plot, if you want. Why? Because if I use f of Q sub I, this is the X sub I, which represents probability, values between 0 and 1. And if I do the Q2 plot, of the points Q sub I and let's call this F empirical. Okay, I'm not going to do it like that. I'm going to say something simpler. And the simpler thing is the following. And that's also a justification for this. If we take the random variable Q, which is F inverse U, where U is the uniform distribution that gave me these points, then the CDF of Q is actually the known CDF F, the given CDF F. And here's the proof. The probability that Q will take a value less than or equal than A is actually the probability that F inverse of U will take a value less than or equal than A, which is actually the probability that the function with the random variable with a uniform distribution will take a value less than or equal than F sub A. To move from this inequality to this inequality, what I use precisely is that F is strictly increasing, and therefore it's invertible. So I just use the theory of inverse functions. So that's a number now. And that's a probability number. And since U has the uniform distribution, that number F of A is going to be between 0 and 1, is actually going to be equal to F of A. And that's a justification. So I know that this random variable will have the known distribution. Therefore, if I take the data points by using the inverse, as I have the inverse of F of the given CDF, then those data points will actually be a realization of the random variable Q, which has precisely the known distribution F, the known CDF, the given CDF F. So if we want to make this simple, let's say that F is the standard normal, that F is phi, the CDF of the standard normal. What would be my points Q? My points Q would be precisely phi inverse of the x sub I. So you would see those points to essentially be accumulated very close to 0 and disperse as we go further away from 0, positive or negative. Okay, so this is one way to create to create this particular distribution. So finally, I want to show you how to create a so-called white noise, an image with a white noise. So an image with a white noise, you want to name n by n image, which would be white noise. Every pixel will be exactly created the way I prescribed here. You will take the x sub I, which is between, take x sub I, a realization, well, let's call it ij. Now, a realization of the uniform distribution between 0 and 1, and of course I will be, and both I and j will be between 1 and n, because now you want pixels, and qij, the value of the ij pixel, will be a number which is given by this. You take the inverse of the CDF of the standard normal distribution. Of course, that's quite complicated because you have the tables to do, and you take that inverse, you take the value of xij, you take the inverse, you calculate this. This is a number between 0 and 1. And if you want to depict that in grayscale, well, just take these values and scale them linearly between 0 and 255. And you have your grayscale image, and this is how you would create a n by n image, which is white noise, and it would look like those, like turning on your TV, but no, without tuning the TV to any station. This is exactly what you would get. Random numbers have played a very, very important role in cryptography, and there's lots of things I can actually say for cryptography. I'm not going to say a lot because it's getting late, but it played a very big role in the Second World War, and subsequently the Enigma machine was one of the tools that actually, if we look at a picture here of the Enigma machine was a typewriter like this. Doesn't get bigger. And it had rotors. It got bigger. Yeah. And it had rotors. So here you would use this keyboard to type, and the rotors were turned into set combinations. And when you had a set combination, the set combination was producing a shift, actually was producing a random shift because it was using a random number to the keyboard. So essentially the entire keyboard was being permuted to understand, let's say that if there would be no permutation, the first key would be A, the second key would be B, the third key would be C, and so forth and so on. As you see here, you have you have numbers from 0 to 10, and you also have, no, actually you don't have numbers from 0 to 10, you have, this was the Army's, the German Army's Enigma machine. This had only the 26 English letters, and you would have 1 being assigned to A, and 26 being assigned to Z, Zulu. And each time you were introducing a permutation, that permutation would shift by a certain integer number between 0 and 26 the entire keyboard. And this was happening actually several times during the encryption of the message. So to produce these numbers, actually there was a set combination that was used in a set hour of the day or during a day, and those combinations of the rotors that were produced actually random numbers were being included in the text, in the text that was the source code and was coming with the Enigma machine. And there were only a certain number of combinations of the rotors that you could use, that the operator could use to encode the message. Then the decoder would know the message, would know, well, probably which combinations would be used, and would search with these combinations to decode the message. There was also a little bit of the message that was there to help the decoder to see which actually combinations were being used. The Enigma was very complex. It was electromechanical, And it was actually followed by several other combinations, with several other encrypting machines. The Russians had encrypting machines. The Enigma was first created in the First World War, and the first ones who broke the Enigma of the Second World War were the Polish cryptographers and actually Polish code breakers, and these tipped the British because the British were facing a very big problem. The Enigma machine was the machine that was used to communicate encrypted messages between the Allied, the submarines, the U-boats, and well, here is a U-boat, and that's actually the U-30, which opens the war in the Atlantic, as I would say. It sank the steamer Athenia with a mad loss of life, about 160 people, I think, because the Athenia remained on the water for almost a day. That gave plenty of time to put all the passengers and most of the crew in the lifeboats and evacuate them safely. And that actually created a confrontation between the British and the U-boat and the German Navy, of course, that actually Hitler wanted to avoid at the very early days of the war. Still, the war was not a war with the British were not already dragged in the war. The war was between Germany, Poland, and France. Still, when the Athenia was sunk. So U-boats were communicating with the headquarters where Karl Dönitz, whom I don't think I have a picture of Karl Dönitz here, was the U-boat general commander. He had a tight control over his crews, and he was communicating therefore very often during the day using this machine. And therefore, it was very important to see for the Allies to know where those boats were being placed. Now, during the early days of the war, actually, there were areas that were quite well patrolled. For example, this area was patrolled by aircrafts. So there was some cover. U-boats could be discovered and sunk by aircraft. And here was the Canadian aircraft, the Canadian Air Force that was patrolling. But between the United States and Great Britain, there was here the so-called gap that was not protected by the U-boats, and actually by aircraft. And over there, there was not sufficient number of escorts to protect the convoys, the Allied convoys. So ships were actually preyed a lot. And especially during the first days of the war, the first year of the war, 1941, merchant ships operating between the United States and Great Britain were traveling alone, praying that they wouldn't be discovered. Breaking the code was a very critical part of the Battle of the Atlantic, because had the supply lines of Great Britain collapsed, then the war would have had probably in Europe a very, very different end than what we are accustomed to know now. The Battle of the Atlantic claimed many ships. Most of them were sunk by U-boats. The British Navy had the biggest numbers. You see here in the numbers, almost 3,000 ships. Even Greece had a lot of ships lost in the Battle of the Atlantic, although Greece didn't even have a big navy, not as a big navy as British Empire and the United States. The casualties were many, and this is something we don't often talk when we talk about the Battle of the Atlantic, but there were many merchant seamen who were lost because of the attacks of submarines. In the early days of the war, submariners who actually should not be confused, with the SS or not even with the Wehrmacht. They had a code of honor when they were operating, and in the early days of the war, they were assisting the crew members of the ships that were lost. They were basically putting them on the lifeboats or helping the lifeboats that were capsized to be turned upright. They were giving them water, food from their own supplies, which were sometimes quite limited, and a compass bearing to the closest land. However, there was one remarkable incident, the Laconia incident, where that passenger liner, which was thought mistakenly to be a trooper, it was thought mistakenly to be a trooper because he was zigzagging and also had guns and actually it's aft. This was a Cunard liner. Cunard was the competitor of the White Star Line, which owned the Titanic, of whom the sinking we celebrate we commemorate. We don't celebrate the sinking. We commemorate in early next month. She sank, and it's actually one of the biggest losses of life. There were about 1,650 people who perished as a result of the torpedoing of Laconia by, I think, U-boat 105. We ought to give the credit here U-boat 156 torpedoed Laconia. The Laconia was close to the Ascension Island, and if you see my map here, my map puts the Ascension Island somewhere here. The ship was sailing from the Suez Canal past south of Africa and all the way to England. It was carrying some passengers, about 80 passengers, but it was carrying a huge number of Italian prisoners. The U-boat, as soon as it realized that there were also Italians in the water, and they realized that this wasn't a trooper. They were expecting to see troops, but instead they heard the cries of women and children and actually Italians screaming in the water. They surfaced, they remained on the surface, and they assisted as many as they could in actually a very, very efficient way. Captain Hartenstein coordinated this action, and in fact, because he couldn't handle the entire rescue operation, he gave up his coordinates and he invited he transmitted in the English language to all ships around in a channel, in a frequency, actually, that would be the emergency frequency that the English Navy and the English merchant ships would use, and the Americans actually would use. He broadcasted the message, petitioning help from all ships that were around, in English, and he gave actually his coordinates, something that he was not supposed to do according to his commands. Well, after that, there was the Laconia incident. That was the Laconia incident that led to complete reconsidering of the policy by Karl Dönitz, but Hartenstein was highly regarded, and despite the offer that despite his desperate attempts to help the passengers that were in the sea and the prisoners, many perished, but many more would have perished had he not been able to provide assistance. So the battle was broken because at some point a great mathematician, Alan Matheson Turing, managed to break, after receiving some initial input from the Polish code breakers, managed to break the British, managed to break the Enigma machine. And in order to do that, they constructed, Alan Turing designed a primitive computer, something like an analog electrical mechanical computer of his time, a precursor of ENIAC, which operated in the Bentley in a secret location of the British intelligence in a park, and they managed to start doing to use combinations to be able to see how this machine would work. His experience from this project helped him later on to define what is a Turing machine, which is a computing machine, and essentially he defined a computer, a device, a machine that can perform computations, computations that any type of computation that we can realize. Then he defined the input, the output. There's a lot of interesting literature about that, but being able to break the code actually allowed the Allied naval authorities to know exactly the positions, the approximate positions of the U-boat, so they were able to steer convoys away, or even alert the escorting ships and Air Force that was occasionally escorting convoys, so that they could outpower the U-boats. In about 1943, the Battle of the Atlantic was turned around, and U-boats started sinking at huge numbers, which made them quite inefficient. So what happened is that the German Navy could not produce well-trained officers or sufficiently trained officers and crew for the U-boats, and of course the morale of the U-boats was very, in 1943 and later furthermore in 1944, was significantly reduced. The U-boat war was essentially came to an end after D-Day, because U-boats were operating out of Normandy, actually out of the west of France, and their headquarters were in France. Well, this is about random numbers, spying, Alan Turing. Alan Turing has a very interesting biography. I advise you to read about him a little bit. He was a fascinating personality, and someone who was lost early enough in his life, but he offered so much. Well, I guess this brings our recording to the very end. Thank you for this, for attending my little amateuristic discovery channel, and I wish you a great day.